Good afternoon, this is Engineer Lagos, and today we will discuss decoders under our subject ECE 3111 or Digital Electronics 1. To start our discussion, first we will learn our learning objectives. At the end of the lecture, the students should be able to first design different types of decoder using logically. Two, create a decoder prototype using Tinkercad. And three, expand the number of decoder I/O by interconnecting three or more decoders. Now, what is a decoder circuit? So by definition, a decoder is just a combinational circuit which has n input lines and a maximum of 2 raised to n output lines. Meaning to say, if you have one input, okay, the number of outputs will be 2 raised to 1. If you have two inputs, and the number of output will be 2 raised to 2 or equals to 4. Now, one of these outputs will be active high, but it depends on the combination of the input present. That is, if the decoder is enabled. When we say enabled, meaning it detects a particular code. And that particular code will be uh, projected in the output of your decoder. Now, the output of the decoder are nothing but min terms of n input variables when it is enabled. Block diagram. These are the block diagram symbols of our decoder. So these are the block diagram symbols. Now, the first diagram is commonly used symbol that is a block with n inputs, and you have here the active low enabled pins, and then you have your 2 raised to n output. So on the right diagram, you have here the symbol for the decoder, which is a rhombus. Now, if you will notice, now, you have three inputs and how many outputs? If you have three inputs, you of course that is 2 raised to 3, or you have 8 outputs. Okay, and the output will depend on the combination of the input signal. Now here are the different decoder IC. These are just sample decoder IC. Okay, more of this. Now we will more of this will be discussed in our future topics. Okay, the first IC here is an octal decoder. So when you say octal decoder, the output, the input, is 3, and we have 8 as our output line. So meaning 3 inputs with 8 outputs. The 3 inputs are binary, and the output will be the equivalent in octal. Like for example, if your input is 0, 0, 0, definitely it will have an output at y0. That is the equivalent in octal. Okay, and also the next figure in the center, we have the BCD to 7 segment detector. So in this BCD to 7 segment detector, this is used, to and connected. This is used to drive our 7 segment LED. Okay. So how many inputs do we have here? We have 4 inputs, A0, A1, A2, and A3, and the output will be from A to G. So from A to G, that's the input. That will represent your 7 segment. Okay, now we will be tackling this. Okay, we will be using this now in our future activities. We also have here BCD decoder, 4 to 10 lines. Okay, so the output is 10 and the input is 4. So when I say BCD decoder, the input, like for example, if the input is 0001, 001, meaning your output will be at y1. So here you have your output 1. Okay, now we go to the next slide. So in our next slide, I have here the simplest line decoder with enabled pin. So on your right, I have also here created uh, um, the representation in logic gates, the combinational logic gates that will represent a line, simple line decoder. So um, let's go back to our presentation. Here we have a truth table. You have two inputs. They are the A, so that is actually the select lines or the select output of your decoder. And EN here is the enable pins. So meaning to say, um, the decoder will only have an output, okay, if it is enabled. Okay, if the enabled switch is activated. Okay, okay, that's it for our decoder. So our input decoder. So we will try it later on. Now, going back in our schematic diagram, okay, in our logic circuit here, you have here A as your input, and EN here is your enabled pin. This is also an input, and you have two outputs. So we count our input as 1 and our output as 2 raised to 1. So this is the configuration of our uh, circuit. So how did we get this combination? Simply by analyzing our output. Like for example, let's focus on y0. So we will focus on this output. Okay, in y0, okay, y0 will become logic 1 if, okay, this input will be the combination. So the combination of this input is just a complement. Okay, I will be referring this as a complement because this is 0. Multiply that by En. This is your mean terms, as defined in your um, definition a while ago. So this is E complement multiplied by En. So this is actually your output. Okay. Now, let's focus on Y1. So if Y1, uh, if, if if Y1 will have an output of logic 1, so meaning to say, you have an input, which is A equals to 1 and En raised to 1. So meaning to say, we can represent that as A multiplied by En. That will be the mean term representation of our output. Take note of that. But now, if your enabled pin is disabled, the output will be equal to 0. Okay? Whatever the combination of your input is. So X here will be your don't cares. Okay. So let's try the analysis. Let's try this now using the circuit on the right. Okay. Now, if I'm going to turn on the enabled pin here, so Y0 will light up. So we'll turn on also. So this will be turned on because A here is logic 0. A is low. So once A is high, okay, Y1 will be turned on. Take note of that. So 0 means Y0 for A. 1 means Y1. So if you will notice, your switch A here is just here to select what will be your output. Where are you going to put what output are you going to activate. So that's the purpose of your A here. This is actually your select output line. Okay. Now take note when when the enabled pin is disabled or deactivated. So um when pressing A as your input, 0 or 1, it does not affect the output. Meaning to say, there's no output when the enabled switch is deactivated. So that is your 1-bit line detector. So this is actually your 1-bit line detector. So the equivalent circuit, the equivalent circuit is this one. This is now the created block diagram. So in this created block diagram, I have here my input as A and my enabled pin as EN. So this is 1 by 2 decoder. It means you have one input that is A and two output that is Y0 and Y1. Okay? So if I'm going to turn this, activate this switch, okay, Y0 will turn on because A here has an input of logic 0, means this line is selected. Okay. Now, if I'm going to turn this on, okay, A becomes 1, so this output will be selected. Okay, that's the basic principle of our uh, 1-bit decoder. Okay, now let me erase this part first. Then we proceed with our presentation. Now, okay, so actually now we already done this one. Let's skip this. Now I have here 2 to 4 decoder with enabled pin. So take note, I emphasize this enabled pin because you can actually design a 2 to 4 decoder without this enabled pin. And this enabled pin is very important in designing your logic, your decoder. So in real world decoder, in real components, there is always an enabled pin. Okay. Now here is the truth table for a 2 to 4 decoder. So meaning when we say 2 to 4, meaning you have two inputs, which is A, B or BA, and you have 2 raised to 2 outputs, namely Y0, Y1, Y3, Y2, and Y3. So take note that these are your output and this will be your input. Now let's analyze the circuit here. Okay, let's analyze the circuit by taking the mean terms of the input. Like for example, if Y0 equals 1, we'll have an output of 1. Okay, meaning to say this is the combination of its input. So you can derive this as A complement multiplied by B complement multiplied by the enabled pin. So that is the mean term now of Y0. Now for Y1, so try to look at the combination for Y1. Let me change the color of this. Let me use blue. So for Y1, you have this combination. Okay. The combination is A is equals to 1. So meaning to say this is A. B is equal to 0, meaning this is B complement. And E raised to E multiplied by E n. So that is the enabled pin. Now for the next output, which is Y, this is Y2. Okay. So the combination of this is, okay, we have A0, so meaning A complement. We have B1, which is B, and we have the enabled pin, which is EN. Okay. Now for the last min term, let me use the black pen. Okay. So the combination is all logic 1. So meaning to say this is A times B times E So that's how you design the logic circuit here. Okay, this is uh, based on the mean terms of the output. Okay, that's how you design your decoder. So if you want to design 3 to 8 decoder, you can use this method. Okay, or you may use K mapping if you want. So let me erase this one and let's try. Now I already created 2 to 4 decoder. Let's try if it's here. Let's check now if my 2 to 4 decoder that I have created is here. Okay, it's already here. So this is my 2 to 4 decoder, where A and B are the outputs and Y0 to Y3 are, I mean, where A and B are the inputs and Y0 to Y3 are the outputs. And still you have your enabled pin. So enabled pin is very important no, in our discussion, especially in creating your design. Okay, now let's analyze now this circuit and compare the result now to our truth table on the left. Okay, now if I'm going to turn on okay the enabled pin, assuming now let me turn this off, assuming our input is 0 0, and let's turn this on. Now based on our truth table here, now the output is at Y0, which is 1. Take note of that. Okay, it's here. It's 1. That's the output of your decoder. Now, when two inputs are 0 and the pin is enabled. Okay. Now, let's turn A equals 1. The output will change to Y1 as indicated here in our truth table. Okay. Now, if I will switch this off and turn on B, the output becomes Y2. So this is actually 0, 1 in binary, and that is equivalent to 2 as your subscript. Okay? And now, if I'm going to turn on both inputs, okay, the output will be at Y3. Imagine now if I will erase this first. If I will turn on both inputs, this will be the equivalent of this is 1 1 binary, which is equal to 3 in decimal. So that is why this is labeled as Y3. All right, so that's it no, for our 2 to 4 decoder with enabled pin. Later on, you will be designing a more complicated circuit using the 1-bit decoder and the 2-bit decoder. This is your 2-bit decoder because you have an input of 2 bits. Okay, now let's proceed to our equivalent circuit. This is the IC that I have created a while ago. This is the same no, in our PowerPoint presentation here. I just copy this and paste it in our presentation. Now, let's try our created IC. So, you already know how to create an integrated circuit in our Logic Leap. Okay? So, no need to explain that one. Now, what we will do here is what we will be doing here will be to analyze the circuit, compare the circuit to our previous circuit, and we will compare the result based on our truth table. Now, enabled pin is selected. So this is enabled, meaning to say the output is activated. Once it is enabled, the output is activated. That is why it is called output enabled, meaning to say once it is activated, now the output will be enabled. So meaning you will have an output. Like for example, if I press switch A, I will turn this on. This will be logic 1. 0, 1 will be Y1. And then 1, 0, 1, 0 will be Y2. And 1, 1 will be Y2. So this is it no, for our 2-bit decoder. Or sometimes we call this as 2 to 4 decoder. That is why in my IC, I label this as 2 by 4 decoder. So that's it. Okay. Now, for our, let's go back to our presentation and try to solve these design problems. Now, our first design problem is to create a decoder. Okay, we will create a decoder with active low enable, and outputs. Okay, now it means that you have an active low enabled pin and output. So the output is active low. When we say active low, when it is activated, it will have an output of 0. Let's try this in your truth table. This is an active low enabled outputs, enabled and outputs. Actually, no, I so enabled pin. I will put here enabled pin and outputs. It means now you have an active low enabled pin. This is your active low enabled pin. I will mark this one. This is your active low enabled pin as indicated here by the bubble. So the bubble that is indicated is the representation of active low, meaning to say if you put logic 0 here, it will activate. It means it will be active when a low signal is present. So meaning to say if this is 0, 0, okay, if all of this is 0 and this is enabled, take note, this is 0, this is enabled, meaning to say the output will be at y0. So let's label this as y0. Okay, output 1, output 2, output 3, output 4. Doesn't matter. So let's just call that as output 1, output 2. And the rest of this will be logic 1, as indicated here. So for an active low decoder, it means that the enable pin is active low and the output pins are also active low. So meaning if this is 0 means it is enabled, you will have an output. Okay, but the output is also active low as indicated here. Now, most of the IC that we will be using, especially a decoder IC, are active low. No, you will learn that later on because you will be designing an active low, a real IC using active low, a real active low decoder IC. You will be designing that later on. All right. Now, we are going to create a decoder with active low enabled pin. So let's put here pin and outputs. Okay, meaning to say, for active high, we can call this circuit as active high because it is activated when a high input or output is present. Like for example, this is an active high because it generates a logic 1 now and the rest are logic 0 when the enabled pin is logic 1 also. Now, we will be designing this circuit based on our circuit here. Okay, based on our circuit. Let's start by creating a min term here. So let's focus on y0. Now for y0, we have these combinations of input. Okay, that is a combination of our input. So we have here 0, 0, 0. So meaning this is A complement, we have B complement, and we also have what? En complement. Okay. So meaning the output is 0. Now, we can represent that using our logic gate. Now, take note, I will be using, in this case, now I will be using an AND gate. Okay, let me put an AND gate here with 3 inputs. Okay. How many NAND gates do we need? That's the question. So by inspection, we need four NAND gates. Okay, four NAND gates. So I will copy this one, duplicate, and then copy. These are my NAND gates. So NAND gates, no. I use NAND gates because no, I want my output to be active low. Now I will copy this and paste it here. Paste it here. Paste it here. So this will be my output. So let me connect now our NAND gate to the display. Okay. Now I have here two switches. Okay. Let me arrange this here. Let me put the switch here. These are my switches A and B. So it's better if we are going to label this now. So this is my A, copy, and this is my B. And of course, I will copy this, okay, and label this as enable. Okay, that is enabled, but okay, take note, we need to use active low, enable, okay, active low. So that is why I put E complement. So that is E and complement. So that's the representation. Oh, by the way, no, this is not what I want. I want to put a label here that is E complement. E and complement, meaning to say, it will only activate no, if I will put an active low signal here. So meaning, since this is an active low, I must put a NOT gate no, here. So this is my NOT gate, and this will be connected to all of the pins no, in my um, IC. So let me arrange this now so that it will look neat. It's my arrangement. Okay, now that is the connection. All right, one more. So okay, that's better. Now since we are also using the inverter to represent this, we get this first to represent intrinsic control B. Okay, okay, no. Okay, this is to represent my complement input. Okay, this is A and B, and I have here a complemented input. Okay, let me adjust it here. So I know no, creating this type of circuit is not that easy because it requires concentration. All right, now let's proceed with our first mean term here. So I have here A complement, B complement, En complement. So En is already complemented and it's now connected to Y0 to our NAND gate. So what what we'll be doing now is to connect these two. Okay, take note this is A complement and this will be B complement. Okay. Right. So let me label this one as Y0. Let's label this as Y0. Now, let's proceed to Y1. Okay, I will put Y1 here. Let me label this as Y1. Now, for Y1, okay, for the input of Y1, we have this input. So we have A, I will put it here. We have B complement, and we have En complement. Okay, now let me connect it here. A here is not complemented. So I'll put it here. I'll adjust this. Put it here. Put it here. That's my A. Okay. For my B, B is complemented. So this is B. Let's put it here. That's a complemented B. Let me arrange this. That's it. That's my arrangement. All right. Nice. Okay, now I have connected Y0 and Y1 to the corresponding inputs. Now we go to the next combination of the input for Y2. So for Y2, we have a A complement, we have B, we have E, and complement. Okay. Now let's copy this one and change the name to Y2. Okay. For my Y2, we have A complement. So this is A complement. Adjust, make it look good, and we have B. Okay, we have B. Okay, and this is my B, and also no E and complement is actually connected. Now, the last one will be 110. So meaning to say this is A, B, and this is E raised to N complement. Okay, so that's it now for our mean terms. Now let's go back to our circuit here and connect. Okay, connect this to A. Oh, what happened? So we connect this to A. Here is A. And then adjust. And then adjust. Nice. And then I will be connecting this to B. By the way, now I have, why is this, let's go back to Y3. So Y2, I mean, let's go back to Y2. But first, no, let me copy this. And put, change the name to Y3. This is Y3. Okay, that's it. Now for my Y3. And let's go back to this connection. Let me delete this one first. Okay, because this should be connected to this line. Okay? This is a positive B, right? So this should be connected. Why is this not connecting? Here. All right, so let me arrange this one here and here. All right, so that's it for my circuit. Okay. Take note. Okay. Let's simulate this one. So take note, no? The enabled pin here is logic 0. That is why you can see the output here. And the output here, since the inputs are logic 0, okay, meaning to say it is at Y0. But the output in Y0 is 0. It means it is an active low output. Okay, once this pin is disabled, or I will put logic 1, meaning logic 1 will disable the output. It means once the output is disabled, all the outputs are logic 1. So this should be logic 1. Sorry for that. This should be logic 1, 1, 1. So I got not changed, but this one will be all logic 1. Take note of our truth table. Okay. So now let's create. Let's change the input here. Let's say this is 1, and we will enable the IC. So Y1 will be logic 0. Okay, change this. B is equals to 1, then Y2 will be logic 0. All 1, Y3 will be logic 0. That's the design for uh, the 2 by 4. And this is a 2 by 4 decoder with active low outputs. So active low outputs. Now, let's create an IC out of this. Before creating an IC, you must create an export name. So I will click here. This will be named as A. This will be named as B. This will be named as E complement. So I will name this as E complement. This will become Y0. This will become Y1. This will become Y2. This will become Y3. Okay, now highlight and then create an integrated circuit. Take note, now here and now, a E complement is present. So we can label this as 2 by 4 active low. Decoder. That's my active low decoder. So 2-bit decoder. That's my file name. I will label this active low. All right. Let me erase this one first. So take note of the outputs. No, when uh, when the input, when the enabled is uh, logic 1. So this should be all ones. Okay. So create an IC, just click create, and you have now a 2-bit IC, okay, which is an active low decoder. All right, now that's it for this problem. Let's proceed with this problem. So create a 3 to 8 decoder IC using 1-bit and 2-bit decoders. Oh, so according to the diagram here, okay, this is an active high IC, active high, right? So we already created these ICs. Let me have my 2-bit IC, okay, and then my 1-bit IC. So to create this decoder, a 3 to 8 decoder, we need a 2 by 4 decoder. 2 by 4 decoder. Okay. Now, the first one here, the first IC here will select which of the two will be enabled. So meaning to say, now this output will be connected to the enabled input of this IC. Okay. Now let me put a toggle switch here that will represent my inputs. And this will represent my input. So how many inputs do we need? We need 3 inputs. Okay. The first input is for A. Let me label this. Okay. The first input is for A. The first switch is for A. Copy. That's it. Okay. We paste. No. Let's just click and drag here. So here we have C and another toggle switch for our enabled pin. So this is our enabled pin. So take note, we are creating an active high 3 by 8 IC. Okay, now this enabled switch now will be connected to enable. Okay, A here will be connected to A. B here will be connected to B. Okay, B here will be connected to switch B, and A here will be connected to switch A. All right, so let me arrange this so that it will look nice. Okay, that's it for my enabled pins. All right. So for B, let me arrange this for a while. That's for my B. Let me adjust it here. All right. So that's my B. And another B. Okay. Now for my A. Let me put my A here. Oh, another A. This is my A. Okay. That's it. So the switch no looks nice. Now the input for my 1x2 decoder will represent your C. Take note of that. And we need output for 8 bulbs. Now, let me arrange the bulb here. 1, 2, 3, 4. So this will represent our outputs. 6, 7. And we will test now if we have successfully designed the circuit. So this will be my Y0, Y1, Y2, and Y3. This will be my Y4, my Y5, and my Y6. The last one will be Y7. Okay, now let's label it completely. So I have here Y0, and then we have here Y1 and Y2 because we will be testing this. Of course, we still have Y3. We also have here Y4. You just experiment on this now in your design laboratory because I will be giving you a design laboratory now from this topic. This will now become Y6 and this will be Y7. Okay. All right. Now let's try. Let's enable the IC. So when the IC is enabled, when 1x2 decoder is enabled, meaning to say this letter C will select Y0. Y0 is selected and then it enables the 2x4 decoder. So this 2x4 decoder now will be enabled and it will display Y0 because of the combination of A and B, which are zeros. Okay, so that's how you explain it. Okay, now let's change this to this IC. Take note, I am not changing the values of A and B. So now I will select Y1 in my 1x2 decoder. 1x2 decoder is selected. This time, Y4 is turned on because here, now this IC is selected. Okay, because of this switch or this IC. This IC is now selected because the output of Y1 enables this IC. And since this IC have an input of 0, 0, now the output will be at line Y0. So that's the explanation. Okay. Now, if I'm going to change this one, okay, this will become at Y1. Okay. Okay. This will become Y7. So technically, this will represent your binary 1, 1, 1, and the output is Y7. Okay. Now, if I'm going to change this to 101, let me change this to 101. 101 is obviously equal to 5. Okay. And this one is 101, which is equal to 5. Okay. Now, if I'm going to disable this, I will select, now, if I will change the value of C equal to 0, let me delete this one. This is now 0, 0, 1. So meaning to say, this IC is now selected because Y0 will enable this IC. So That is why Y1 is turned on, because the combination of B and A here is equivalent to 1. So that the output will be at Y1. Okay? So that's the explanation on how the expansion of decoders is being done. All right. So I hope now you've learned something from my discussion about decoders. Now, this is your challenge problem. So actually, now you have to do this now after watching the video, because this is not part of your uh, design problem. This is just the challenge problem. Okay, challenge yourself now to create or to design a 74138. This is our 74138 IC. 74138 IC. This is an actual IC. So take note, the actual IC have three enabled pins, 4, 5, 6. So take note, enabled pins. Okay, so E1 and E2, look at this, E1 and E2 are active low, and E3 is active high. Okay, now if you will notice, the output here, the output are also active low as indicated here. So this is actually an active low IC. Okay, because this is a real IC, meaning to say the outputs are active low. Of course, there are also ICs that the outputs are active high, but this one is an active low IC. That is why, in our previous discussion, we designed 2 by 4 active low decoder. So your task for today is uh, to design a 3 by 8 active low IC that will be represented by 3 enabled pins. Okay, so you have to create an IC out of this. Okay, that's your task for today. So that's it. Okay, that's it for my discussion. Now I hope you've learned something from my very short discussion.